Right. Last time we left off by saying that even if an object isn't rotating in the normal sense, we can say that it has some angular momentum if we think, in this case especially, about how a point object can have angular momentum about a certain axis. If we consider this axis, this right here, to be the rotational axis, then this certainly does have some rotational motion because it has a mass, it has some velocity, and it's a certain distance away. Okay, that's all I'll say about that. But there is a way for us to calculate the initial angular momentum. So, what we're going to say here, and I just realized that I have these in the wrong places. There we go. What we're going to do here is we're going to say that the initial angular momentum is equal to mv naught times r, and that in turn is equal to I times omega. This is the angular momentum for a point object. This is the angular momentum for the entire object as it continues to rotate after the collision happens. Now the key here is that we don't quite know what the moment of inertia is, but we can build that up because we know that the moment of inertia of the mass must just be mr squared. Okay, because it's a point object. And the moment of inertia of a rod, which remember you don't have to know, you don't have to memorize all these different moments of inertia. They will be given to you as needed. The moment of inertia of a rod like this is equal to 1/12 mr squared about its center. And you know what? Let's not even call it r. Let's change that to an L. Okay, 1/12 times the mass of the rod multiplied by its length. So let's start subbing these in. We know that this is mv naught. R is the distance away from the axis of rotation. That would be L over 2. So I'm going to put in an L over 2 equals, let's see, I is, as we know, let's see, that would be L over 2 squared plus, because we can just add moments of inertia if we need to, so plus 1/12 L squared. This comes down to, let's see, mv naught L over 2 equals ml squared over 4. And this would be capital ml squared over 12. We've forgotten the omega. Sorry, didn't mean to do that. It is I omega, not just I. In order to add these two together, we could get them with a common denominator. So let's actually do that. Let's do mv naught L over 2 equals, let's see, we need to multiply both these by 3. 3ml squared plus ml squared over 12. You've noticed by this point that everything is basically just everything we're doing is basically just algebra at this point. So let's see what we're going to do. Oh, and omega. So what we're going to do here is say that this is now equal to, let's pull the let's see here, let's pull the L over 12 out. Yes, let's pull the L squared over 12 out to this side. L squared, let's put the omega in front too. Omega over 12. This becomes just 3m plus big M. And that's equal to mv naught L over 2. We have an L on both sides. One set of L's can cancel. This 2 and this 12 can cancel, and this becomes 6. So if we divide both sides by, or let's see, if we multiply both sides by 6 and divide by L times 3 little m over m, we end up with this. Omega equals 6m v naught over 3 little m plus big M times L. and that is the equation for the rate at which the rate of the angular velocity. Okay, the angular velocity of this. Notice that that is ugly, very, very ugly compared to this. They're much simpler. However, it is accurate, okay? A lot of times, if you have things that are kind of lopsided, you're going to get results like this. Really, it's just algebra to work through, okay? The more you practice it, the less intimidating it will get. This just goes to show you that not only in a situation like this can we find the velocity after the collision, we can also find the rate at which the system rotates. Okay. So here's what we're going to look at now. When can we say that these things are conserved? Okay. Well, you really just have to ask yourself a couple questions. Is the object free to move linearly? And are they free to rotate? In other words, are they allowed to rotate without any net external torques? And are they allowed to move linearly without any external net force? If the first question is true, if the answer is yes, then P is conserved, as long as there's no net force. If the object is free to rotate, then L is conserved. Okay? So, we just saw an example where both were conserved. You have been doing examples all year where linear momentum is conserved, and we haven't really looked at angular momentum. There are examples where you can have angular momentum be conserved, but not necessarily in that system linear momentum be conserved. So let me give you an example of that. Example of linear momentum not being conserved. Imagine this. Imagine that last example. An object hits a rod that is pinned down at one end. L is conserved, but the pin exerts an outside force F on the rod, allowing it free rotation but not translation. In other words, it can't move freely, it can't leave its spot, but it can rotate freely. Okay, that would be an example where where angular momentum is conserved at the expense of linear momentum not being conserved. It doesn't have to be like that, but in that situation it would be. Okay, and I've really only just got one more thing for linear momentum in the center of mass. And we've kind of talked about it before, but I just wanted to make a point of it. If linear momentum is conserved, then the center of mass, I'll just write it out. Center of mass does not accelerate. And that is very important to remember. If linear momentum is conserved, if P is conserved, then the center of mass does not accelerate. Okay? So, angular momentum, there's really not that much to it. It's very much an extension of linear momentum, but applied to systems that are rotating. Take a look at some of the problems and let me know about your questions, and I'll see you for the next topic. Bye.